Hello friends, welcome to my lecture on applications of Z transforms. So, this we will cover in two lectures. This is first lecture on application of Z transforms. We know that the differential equations model those processes in which we know relationships between changes and or differences rather than the rates of change which leads to the differential equations. Now, these differential equations arise in those situations where a sequential relation exists at various discrete values of the independent variable. The recurrence relation that we obtained while solving the differential equation by power series or Frobenius method are also difference equations. Similarly, numerical solution of differential equations also leads to difference equations. Now, in control engineering, often the input is in the form of discrete pulse of short duration, and the radar tracking devices receive such discrete pulse from the target which is being tracked. So, difference equation is a relation between the differences of an unknown function at one or more general values of the argument. For example, let us consider delta by n plus 1 plus by n equal to 2. This delta is the forward difference, and then you can also consider delta by n plus 1 plus delta square by n minus 1 equal to 1. Both of these equations are difference equations. These two equations can be put in the following form. We know that delta of fx, the forward difference, delta of fx is fx plus h minus fx. So, using this definition, delta by n plus 1 will be equal to by n plus 2 minus by n plus 1, and hence delta by n plus 1 plus by n equal to 2 gives us by n plus 2 minus by n plus 1 plus by n equal to 2, which is so alternately the difference equation 1 can be expressed like this, and similarly the equation 2 is delta by n plus 1 and plus delta square by n minus 1 equal to 1. So, here we can write it as delta by n plus 1 is first order forward difference. So, we get by n plus 2 minus by n plus 1, and delta square by n minus 1 here is delta square is second order forward difference. So, this will be delta of delta by n minus 1 equal to 1. Now, delta by n minus 1 is equal to by n minus by n minus 1, and so delta of delta by n minus 1 is equal to delta of by n minus 1, which is equal to delta by n minus delta by n minus 1, but delta by n is by n plus 1 minus by n, and here this is by n minus by n minus 1. So, we will get by n plus 1 minus 2 by n plus by n minus 1. So, let us substitute the value here. So, by n plus 2 minus by n plus 1 and then plus by n plus 1 minus 2 by n and then plus by n minus 1 equal to 1. So, this cancels, by n plus 1 cancels, and we get by n plus 2 minus 2 by n plus by n minus 1 equal to 1. So, the equations 1 and 2 can be alternately written in these forms. So, the equations 1 and 2 can be also written as by n plus 2 minus by n plus 1 plus by n equal to 2, and by n plus 2 minus 2 by n plus by n minus 1 equal to 1. Now, let us discuss how can be determine the order of a difference equation. So, the order of a difference equation is defined as the difference between the largest and the smallest argument occurring in the difference equation divided by the unit of increment. So, let us see here this equation which is alternate form of the first equation number 1 and this one, and this equation which is the alternate form of this equation. So, here we see that the largest argument is n plus 2. Okay. So, let me call it as equation number, this is equation number 3 and this is equation number 4. So, in 3 largest argument is n plus 2 and then the smallest argument is n divided by the unit of increment. Unit of increment is 1, we have n plus 1, n plus 2. So, this is 2. So, this is of second order and here the largest argument is n plus 2, the smallest argument is n minus 1 divided by the unit of increment is 1. So, we get here 3. So, equation 1 is of second order while equation 2 is of third order, or you can say equation 3 is of second order and equation 4 is of order 3. Now, solution of difference equation. So, when we have a difference equation, the solution is defined as an expression for yn which satisfies the given difference equation. The general solution of a difference equation is that in which the number of arbitrary constants is equal to the order of the difference equation. So, suppose we want to solve this difference equation 3, then its general solution must involve 2 arbitrary constants, because here there are, here the order of the difference equation is 2. Similarly, the equation 4 is of order 3. So, the general solution must involve 3 arbitrary constants. So, general solution will be that solution of the difference equation in which the number of arbitrary constants is equal to the order of the difference equation. Now, a particular solution of the difference equation will be obtained from the general solution by assigning arbitrary particular values to the arbitrary constants. Let us now discuss how we can solve linear difference equation with constant coefficients. A linear difference equation is defined as an equation in which by n plus 1, by n plus 2 etc., that is all by n plus all the sequences arguments by n plus 1, by n plus 2 and so on, they occur in the first degree and they occur separately. Like a linear difference equation with constant coefficients in general will be of this form: by n plus k plus a1 by n plus k minus 1, a2 by n plus k minus 2 and so on, ak by n equal to fn, where a1, a2, ak are constants. So, here you can see this is a kth order difference equation, because n plus k is the highest largest argument and n is the smallest argument. So, n plus k minus n divided by 1, unit of increment is 1. So, it is kth order difference equation and it is a linear difference equation, because by n plus k, by n plus k minus 1 and so on by n, they all occur in first degree and separately. Now, if u1, u2, u1, if u1, u2, ukn are k independent solutions of this equation by n plus k, a1 by n plus k minus 1, ak by n equal to 0. So, here we say that k is the order of the difference equation, k is the order of this difference equation. So, let us consider the corresponding homogeneous part. So, by n plus k plus a1 by n plus k minus 1 plus ak by n equal to 0. If u1, u2, u1, ukn be k independent solutions of this homogeneous equation, then their linear combination c1 u1 plus c2 u2 ck uk is called the complete solution of this homogeneous equation. Let us denote it by say un. If bn is a particular solution of equation 1, if bn is a particular solution of this non-homogeneous equation, then the complete solution of equation 1 will be given by n equal to un plus vn, where un is called the complementary function and bn is called the particular integral. Now, thus the general solution of the difference equation 1 is the sum of the two, that is complementary function and the particular integral. The solution of equation 1, solution of 1 can be obtained by the classical approach, like we just as we solve the linear differential equations with constant coefficients. So, these linear difference equations with constant coefficients can be solved in an analogous manner by the classical approach, but here we will solve them by using the Z transforms. So, we are solving these linear non-homogeneous difference equations with by using Z transforms. Let us see how we do this. So, suppose we consider, so let us consider 4 un minus un plus 2 equal to 0 with u naught equal to 0 and u1 equal to 2. So, we are given this difference equation. You can see the largest argument here is n plus 2, the smallest argument is n. So, and the unit of increment is 1. So, it is the second order difference equation, second order difference equation. And they are given two initial conditions. The conditions are u naught equal to 0, so u1 equal to 0. So, we will get with these two initial conditions we shall get a particular solution of this difference equation. So, what we do in order to solve this difference equation, what we do is we take the Z transform of both the sides of the difference equation and then solve this solve the resulting equation for the value of uz, where uz is the Z transform of the sequence un, and then we divide uz by z and break uz by z into partial fractions in such a way that when we write the corresponding expression for uz, it comes in terms of the known Z transforms. So, that while inverting uz we get the sequence un easily. So, let us say let us take the Z transform, taking Z transform of both the sides. Let me call it equation 1. So, this equation 1. So, taking Z transform of equation 1, we have 4 times Z is a linear Z is possesses linear property. So, 4 times Z of un minus Z of un plus 2 equal to Z of 0, which is 0. So, now 4 Z of u1 is 4 of uz, uz is the Z transform of the sequence un, and here while writing Z transform of un plus 2, let us recall the shifting to the left, shifting of un to the left. So, we know that Z transform of un plus k, where k is greater than 0, is equal to Z to the power k, and then we have uz minus u naught minus u1 by z and so on minus uk minus 1 over z to the power k minus 1. So, let us apply this formula. So, z square into uz minus u naught minus u1 by z equal to 0. Let us make use of the given conditions, u naught equal to 0, u1 equal to 2. So, 4 uz minus z square, and then we get uz minus 0 minus 2 by z. So, the coefficient of z is uz is 4 minus z square into uz, and we get this term minus z square into minus 2 by z. So, plus 2z equal to 0. We can write it as uz equal to 2z upon z square minus 4. Now, let us write uz by z. We break uz by z into partial fractions. So, 2 over z square minus 4, which is 2 over z minus 2 into z plus 2. The partial fractions of this expression is 2 times 1 over z minus 2 minus 1 over z plus 2 divided by 4. Okay, so this is 1 by 2, 1 over z minus 2 minus 1 over z plus 2. Now we can write uz from here. So uz now, thus uz is equal to 1 by 2 z over z minus 2 minus z over z plus 2, and hence u1, which is z inverse of uz, is equal to 1 by 2 z inverse of z over z minus 2 minus z inverse of z over z plus 2. Let us recall that z transform of a to the power n is z over z minus a, provided mod of z is greater than mod of a. So z inverse of z over z minus a will be a to the power n. So here we have 2, and therefore 1 by 2 to the power n, and for this mod of z must be greater than 2, and then from here we get minus 2 raised to the power n. So here also mod of z must be greater than 2. So mod of z must be greater than 2 for this to be true. Okay. So 1 by 2, 2 raised to the power n minus 2 to the power n, we can simplify it further, 2 to the power n minus 1, and then I can write it as plus minus 2 I can take from here. So minus 2 to the power n minus 1, minus becomes plus, so this is minus 2 to the power n minus 1. So this is the sequence un equal to 2 to the power n minus 1 plus minus 2 to the power 2n minus 1, which is the solution of example 1. Now let us take the example 2. So here we have the sequence un plus 2 plus 4 un plus 1 plus 3 un equal to 3 to the power n. Again let us see, n plus 2 is the largest argument and n is the smallest argument here. So n plus 2 minus n divided by the unit of increment is 1. This means the order of this difference equation is n plus 2 minus n divided by 1. So that is 2. This is the order of the difference equation. So this is second order difference equation. Let us solve this. Here we are given the initial conditions, u naught equal to 0 and u1 equal to 1. So the general solution of this difference equation will involve two arbitrary constants. To determine those two arbitrary constants, we are given two conditions, u naught equal to 1 and u naught equal to 0 and u1 equal to 1. So this will give us a particular solution of the difference equation. Now let us take z transform here. So z transform is a linear operation. So z of un plus 2, z of un plus 2 plus 4 times z of un plus 1 plus 3 times z of un equal to z transform of 3 to the power n. Now again let us apply the shifting of un to the left. So z of un plus 2 will be z square uz, where uz is z transform of the un sequence, minus u naught minus u1 by z plus 4 times z of un plus 1 will be z times uz minus u naught plus 3 times z transform of un is uz equal to z to the power z of 3 to the power n is z over z minus 3, provided mod of z is greater than 3. Now let us use the values of u naught and u1 which are given to us. U naught is given to be 0, so uz minus 0 minus u1 is 1 over z plus 4z times uz minus 0 plus 3uz equal to z over z minus 3. Let us collect the coefficient of uz. So, z square plus 4z plus 3 into uz we have, and then we have minus z square by z. So, minus z when goes to the other side becomes plus z. So, z over z minus 3 plus z, and this will give you z square minus 2z divided by z minus 3. Now, let us find uz by z from here. So, then uz by z, it will be equal to z minus 2 divided by z minus 3 into z square plus 4z plus 3. If you factorize, you get z plus 1, z plus 3. So, z plus 1 and z plus 3. So, now we have to break this uz by z into partial fractions and then determine the inverse z transform. So, uz by z, so let us write it as a over z minus 3 b over z plus 1 c over z plus 3. The values of a, b, c can be obtained now. A is equal to z minus 3. So, z minus 2 divided by z plus 1 z plus 3 evaluated at z equal to 3. So, this will be equal to 3 minus 2, that is 1, and 3 plus 1 is 4. Uh, 3 into 3, 3 plus 3 is 6, so 24. So, it is 1 by 24. B will be equal to z minus 2 divided by z minus 3 into z plus 3 evaluated at z equal to 1 minus 1. So, we get this as minus 3 divided by minus 4, and here we have 2. So, 3 by 8, and C we will have as z minus 2 over z plus z minus 3 into z plus 1 evaluated at z equal to minus 3. So, this will be minus 5, and here we will have minus 3 minus 6 into 2. So, 5 by 12, and hence uz by z is equal to 1 by 24 z minus 3, b is 3 by 8, 3 by 8 z plus 1, and then we have 5 by 12 z plus 3. Okay, so now we can multiply by z. So, this gives uz is equal to 1 by 24 z over z minus 3 plus 3 by 8 z over z plus 1 and 5 by 12 z over z plus 3. Now, we can easily invert this. So, let us take the z inverse Z transform. Okay. So, this was un plus 2 here. Okay. So, then hence Z inverse of uz is equal to 1 by 24 Z inverse of Z over Z minus 3 plus 3 by 8 Z inverse of Z over Z plus 1, and then we have 5 by 12 Z inverse of Z over Z plus 3. Again let us recall that uz Z of u to the a to the power n is Z over Z minus a, where mod of Z is greater than mod of a. Let us apply this formula. So, Z inverse of Z over Z minus 3. So, this is 1 by 24 3 to the power n, where mod of Z is greater than 3, and then 3 by 8 here minus 1 to the power a is minus 1, and here mod of Z is greater than 1. So, mod of Z is greater than 3 here, here mod of Z is greater than 1, then 5 by 12 minus 3 to the power n. So, here a is minus 3, and therefore, mod of Z is greater than 3. So, the common region is mod of Z greater than 3, and Z inverse of uz is un. Okay. So, thus un is 1 by 24 3 to the power n 3 by 8 minus 1 to the power n plus 5 by 12 minus 3 to the power n, where mod of Z is greater than 3. So, this is the answer to this difference equation. By taking Z transform takes care of the initial conditions. We do not have to use initial conditions after we have found the solution like we do in the classical approach. So, here this is how we apply the Z transform technique. First we take the Z transform of the given difference equation, collect the coefficient of uz, rest of the terms we take to the right side, divide by the coefficient of uz, and then take the then you write uz by z, and the expression of uz by z is then broken into partial fractions in such a way that we, while multiplying by z, we get the expressions in terms of the z transforms of known z transforms. So that while inverting we get easily the sequence un. So, un here can be obtained like this. In our next lecture we shall discuss some more problems where we will have to be very careful while writing uz by z, because there in the problems the expressions we will have to arrange of uz by z, so that while inverting we get the sequence un very easily. So, we will do that in the next lecture. With that I would like to conclude my lecture. Thank you very much for your attention.